of the course. So so many things are there in that brochure. So the topic given to me is photogrammetry. So photogrammetry is actually covering the photogrammetry in 1 hour is very difficult, because the basics of photogrammetry comes from the surveying also. We have to discuss so many things, and only defining photogrammetry is not sufficient also. So I want to link so many things here in this session, which are there in the scope of the course. Okay. So in surveying, we have seen all of you are civil engineers only. Hello. Okay. So mostly are civil engineers. So from the civil engineering concepts, we have seen the ways to find out the vertical angles. Okay, vertical heights from the vertical angles. So we have theodolite. So using theodolite, we can find out the elevation of any point, RL of any point. And the tachymeter is there. Actually, these are the instruments. I'm seeing there are some people who are not from civil engineering background, but these are the instruments to find out the elevations of any point. Okay, on a map we can see only x and y, xy, the x coordinate and y coordinate, but the z coordinate can also be shown on the map. So to show the z coordinate on the map, that elevation is nothing but the z coordinate, the height above a particular reference surface. Okay, that is called as elevation. So that height can be measured using field instruments such as theodolite and tachymeter. These are some instruments. Okay. And there is one leveling instrument also, which is used to find out the elevation of any point. Okay, we are not going to discuss about how these instruments are used, but as of now, understand, particularly for non-civil engineering people, there are some instruments, field instruments like theodolite we have seen, tachymeter we have seen, and there is also one instrument which is called as leveling method. Using any leveling instrument, elevations can be calculated. And using these elevations, this map on the map, the elevations can be shown as contours. Okay, see on the ground we have on the map we can see the numbers on the right hand side. You can see these are the elevations of all the points on the ground above a reference surface. Remember, the reference surface can be taken as that is called as a datum. Above the datum, what is the elevation of each point? This is a ground piece of the ground. Okay, say suppose 5 means it is 5 meters above the datum surface. It is almost equal to the datum surface. Okay, it coincides with the datum surface. So if you are drawing a line, say suppose here you see 0 to 0, we are drawing a line, and we can draw the lines joining all tens. We can join all the lines. We can join the lines joining 20s. Okay, that means these are the lines joining the points of same elevation. Such lines are called as contours. So these contours can be used to represent elevations on the map. Okay. And there are digitally there are other methods to show the elevations, which are called as digital elevation model. So these are the say suppose you can see the bottom. Can you see my cursor, all of you? Can you see my cursor? Cursor moving on the screen. Okay, so these are the elevations. Dr. Asmuk Chauhan is there. Okay, these are the elevations. Okay, these elevations can be represented. These are the elevations. These elevations can be represented graphically in 3D. Okay, as this. So this model is called as DEM, digital elevation model. Okay, this elevation model can be created from the contours also. Okay, so from the satellite imagery directly also the elevation models can be created, like inframetric synthetic aperture radar. This is a satellite sensor. Using this satellite sensor, we can directly create a 3D model which looks like this. And satellite DEMS, these are the DEMS, digital elevation models. which are directly available in the internet. The source also are given. So using from these links, the elevation model for almost whole of the earth can be downloaded. Okay, but the resolution of these dams are about 90 meters and 30 meters. Okay, if we want more accurate dams, so the dams can be acquired using high resolution satellite data, but these dams are available over the internet at 90-meter resolution. Coming to photogrammetry, okay, photogrammetry is a technique particularly used for generating for elevation measurements. So let me read the line here. Photogrammetry involves precise measurements on the photographs. So photogrammetry is nothing but anything if anything can be measured on the photograph. Photogrammetry, metry is measurement, or okay, metry on the photo, that is called as photogrammetry. So if we are measuring anything on the photographs, that is called as photogrammetry. And these photographs are usually taken using aircrafts. Okay, at the base of the aircraft, a camera is fixed. Okay, so using this camera, when the aircraft is moving, okay, the camera takes the photographs continuously, and these photographs are used to measure the XY and also the elevations. And the contour intervals smaller than 1 meter can also be plotted. Contour interval is, let me go back to this particular slide. You see, contour interval is see here we can see there is a 10-meter contour and there is a 20-meter contour and there is 30-meter contour and 40-meter contour. So the difference between each contour, the elevation difference between each contour here in this case is 10 meters. So using photogrammetry, we can go as far as up to 1 meter also, and also better than 1 meter contour interval also can be plotted. That means that is how accurate the elevations will be in photogrammetry. So in photogrammetry, these photographs are used to be uh, using these stereo plotters or any other instruments for extracting such information. By definition, photogrammetry is a science, art, and technology of obtaining reliable information. Reliable information is the required information from the photographs. It is an art of acquiring the required information from the photographs. The advantages of photogrammetry is it is speed of collecting data. Speed in the sense compared with the field instruments, as we have seen in the first slides. Okay, using field instruments, okay, it takes longer time particularly if the area is very large. Okay, so if the area is very large, using field instruments, it takes a lot of time. Instead, if aircraft is used, aircraft will be flown over the area, and while it is flying, it takes continuous photographs. So thereby the data acquisition will be very fast and relatively very low cost. Low cost in the sense particularly we are talking about the larger areas compared with the field instruments. Okay, it is very easy to work in inaccessible areas where the instruments cannot be taken to. Okay, so very tedious because of the maybe the terrain or whatever conditions. Okay, when photographs are there, the photographs can be taken for any type of area. And omission of details. So there is no scope of any detail, the omission of any detail. So photograph is there. In the field instrument, what happens is we can omit or forget to take some details. Okay, while mapping all these things, so many things, then we'll understand that so few features are missing. Again, we need to go back to the field to acquire. Instead, the photographs are, when the photograph is taken, so it covers the whole area, whatever is there in that area, everything is photographed. So there is no scope of missing any detail. So divisions of photogrammetry, it can be satellite photogrammetry. Satellite photogrammetry is where the satellite takes the photographs. Okay, actually these are not called as photographs, but these are called satellite images. But these satellite images are also can be used in photogrammetry using photogrammetric principles to extract the reliable information. As I said, the next case is the aerial photogrammetry. Aerial photogrammetry means when the when the photographs are taken using aircrafts. Okay, and close-range photogrammetry. Close-range photogrammetry is a case where using normal photograph, normal camera photographs are taken. Okay, these are the three primary divisions of photogrammetry. Taking aerial photographs. Okay, photographs are usually taken along a series of parallel passes, are called a flight steps. I'll show you. See, the aircraft is moving here, aircraft is moving like this, and B is the distance between two exposure stations. Exposure station is nothing but when a photograph is taken at this position, okay, and the next photograph is taken at this position. When the photograph is taken from this position, okay, this is G is the width of the ground which is covered on the width of the area which is covered on the ground. Okay, and when the camera moves to the next position, and this is the position, this is the area which is covered by the photograph. So the overlap region between two exposure stations, this which is called as end lap. End lap is an overlap measured along the flight direction. G is the width of the ground. B is the distance between two flight exposure stations, and this is the end lap. Usually, this end lap is maintained at about 60 to 80 percentage. 60 to 80 percentage. Okay, along the flight line. This is PE is called as percentage end lap. Okay, percentage end lap is calculated by G minus B by G into 100. This is how the photograph, the percentage end lap is calculated. See here, in this photograph. See, this is the flight strip. Flight strip. This is the width of the photograph. This is the width of the photograph. Okay, and there are so many photographs taken like this. There are so many photographs taken along the flight strip. Okay, so all the photographs taken along the flight strip, along this flight line is called as a strip. This is one strip. Second strip is after taking a U-turn, the second strip. These are the photographs taken along the strip number 2. So there is an overlap between the strips also. Okay, such an overlap is called as side lap. Such an overlap is called as side lap. So this side lap is between the strips. Okay, so side lap is maintained at about 30 percentage. So there are photographs along the strip. Okay, and along the strip, if there is an overlap, that is called as end lap. And between the strips, overlap between the strips is called a side lap. End lap is maintained about 60 to 80 percentage, and the side lap is maintained at about 20 to 30 percentage. Okay, shall I move on or any confusion till now? Okay, I move on. And this is how PS stands for percentage side lap. Percentage side lap is this is the aircraft in the first strip number 1, and this is the aircraft in the strip number 2. Okay, side lap is the overlap between the two flight lines. These are the various applications of closed photogrammetry. Okay, in architecture, particularly when mapping, and these are the applications of closed photogrammetry. Remember, see, these are the applications of CRP. CRP is closed photogrammetry. Okay, sorry. And architecture in architectures like for mapping the buildings, particularly there is a concept called as architectural photogrammetry, or where the old monuments, old temples are monumented or documented. Okay, accident studies and what is the amount, what is the damage occurred in accident. That accident mapping can be done using closed photogrammetry. Forensic applications, industrial applications, okay, and underwater photogrammetry. Okay. And underwater photogrammetry is also used to map. Nowadays, drones are used to map, and underwater drones are used to map the river bed, underwater bed, in medical imaging. So all this, the various applications of closed photogrammetry. Coming to total session, of course, I have seen the schedule already. Mr. Chandra Mohan has already taken, but just to cover some other things. Okay. Total session is a combination of electronic theodolite, EDM. EDM is stands for electron distance measurement, and microprocessor. Microprocessor does all the calculations. EDM measures the distance, Utilite measures the angles, and distance. Using angles and distances, coordinate can be calculated. This calculation part will be done using microprocessor. It usually observes the angles and the distances. It computes the distances and also the coordinates. Okay, everything is displayed on the screen, and it has a memory where everything gets stored. The classifications based upon what type of wave is used, maybe microwave or visible light or infrared. Okay, and these instruments are used usually, particularly most of the instruments are visible light, where the medium range instruments, which are called as UDM. On the basis of range of application, okay, short range, which has a range of less than 3 kilometers, medium range is up to 25 kilometers, and long range is up to 100 kilometers. Usually, in most of the cases we might have seen in academic institutions, the short range total stations are available. The characteristics. Okay, I think I'll skip this slide because I hope everything is being already covered by other experts. So usually the range is up to 3 kilometers. Accurate, it is more accurate up to plus or minus 5 mm plus 5 ppm. Operating temperatures and all other things. So as the sorry, this is I got in feet and converted to meters also. Up to 10 feet, the precision is about 1 in 600. Okay, so linear precision. The error is, see the error. Okay. Error will be increasing as the distance is increasing. Okay, so usually the accuracy will be more if the distance between the instrument to the staff is less. Advantage of totalization, so relatively quick collection of data. Multiple service can be performed at one setup. So there, as working in Windows, we can open with many files. In one file, only control data can be there. In another file, some elevation information can be there. In other file, maybe maybe the reference information can be there, or road network, only a road feature can be there. So you at a particular station, we can open one file, take the data from one file, and that data input can be used, that information can be used as an input in another file. So many things can be done parallelly. And easy to perform distance calculations, okay, and simultaneous calculation of project coordinates. Layout of construction site is done quickly and efficiently. Layout can be done. Layout means usually in surveying there are two parts. One is collecting the data, and second is using this data, fixing the coordinate on the ground. Say suppose there is a we wanted to plan a bridge, okay, small culvert, or we'll take a small culvert. Okay, we know we have the map first. So to prepare the map, all the data is taken and the map is prepared. And on the map, we decide where is the appropriate or the best location of the tunnel, of the culvert or a bridge. So on the map, we have the coordinates of the bridge, and these coordinates are fixed on the ground. That is called as layout. Okay, so these instruments can be used to acquire the data and also for the layout. The data can be design data from the CAD programs can be uploaded to the instrument. From the CAD programs, it can be uploaded to the instrument also, and from the instrument also it can be exported in CAD format. Accuracy of totalization, just now we have seen the angle accuracy can be from 1 second to 5 seconds accuracy. The design distance accuracy is also shown here. So developments of totalization. Developments means in totalization we can there is something called as compensator. This compensator will see how much it is out by horizontal plane. We do level. The instrument has to be leveled in both the horizontal and both the X plane and the Y plane. Here you see in the figure this black dot. Okay, If it is exactly the center, the instrument is centered properly, leveled properly, leveled properly. So we can see digitally, digitally whether the instrument is exactly leveled or not. If the instrument is not leveled, instrument can be inclined. If the instrument is inclined, the distance will be erroneous. Okay, the coordinates will be erroneous. Laser plummet. Plummet is an option in the instrument to find out whether the instrument is exactly set over the station or not. So laser plummets. Wireless communication. So the data in the instrument, usually the traditional method is to download all the data using a cable from the instrument to the computer. Nowadays the total stations have come with wireless communication. So data can be exported to any system, or through mail also it can be sent. Okay, or from Bluetooth, using Bluetooth it can be transferred. Using any other technology it can be transferred to any instrument. And graphical view of plot. So on the screen itself, we can see what are the how our data is taken, and internet connectivity is there. Okay, touch screen large display is there. Onboard area volume calculation. So in the field itself, we can find out what is the area covered and what is the volume of the earthwork. See here on the screen, we can see these are the lines. So everything can be seen on the screen in the field itself. And as I said, the images can be taken. There is a camera, so over the image we can see how whether the line is exactly taken properly or not. Okay. Such uh, advanced instruments have come in the market. There are something called as reflectorless totalization. Reflectorless totalization means usually the instrument will come with a reflector. So wherever there is a reflector, instrument is pointed to the reflector, and wherever there is a reflector, the distance will be calculated to that reflector, and also the angles, vertical angles or whatever. There is an option in the most of the total stations where it is called as reflectorless. So there is no reflector at all. So here you see in the first figure, there is an undulation or a rock. So this rock can be plotted. So how much is the undulations? How much is, say suppose there is an earth, there is a landslide. So amount of landslide can be mapped. Okay, amount of earth which has slided. Okay, so that can be plotted. That can be mapped. And also using you see in the next figure, the freshly laid concrete is there. So we cannot ask the person to move on the concrete. Okay, move over the concrete to find out what is the area covered, concreting done. Okay, so using reflectorless totalization, that can be without using only one person will be working with the instrument. And something called as robotic totalizations. Robotic totalization means here you see this is a reflector. Okay, reflector, usually there will be two people working with the totalization. One person will be standing at the instrument, and second person will be standing at the reflector, holding the reflector and moving to the points where the data can be acquired. In robotic totalization, only one person will be working, that too with the reflector itself. So this instrument can be operated. The instrument can be operated from the reflector. There is a panel here. So here, if he says save this point, so instrument will be instrument will save this coordinate in the instrument. Okay, and wherever this reflector is moving, so it will be logged to this reflector continuously. So wherever reflector is there, it is the reflector. The instrument will search for that reflector. So that model is called as robotic totalization. And there is something called a smart station. Smart station is nothing but the totalization with the GPS on top of it. Okay, usually what happens is whenever we fix the instrument on any point, it will ask two things. One is what is the name of that point. Second is what is the coordinate of that particular point. Usually, if the coordinate is known, we input that coordinate, or if that coordinate is not known, we have to assume some coordinate. Then using this coordinate system, the other points will be calculated. Instead of assuming it, if it has got a antenna, GPS antenna. So if we wait for a few minutes, whatever the GPS calculates, that coordinate can be taken as an input to the total station. So it is a combination of both GPS and the total station. Such an instrument is called as smart station. Anything anything you want to ask till here? Any conclusions?
From the participant side, you can drop in the chat box.
Yeah.
They cannot unmute, sir. They can drop their questions in the chat box.
Yeah. In meanwhile, also you can start chatting. Okay.
Fine, sir. Participants, if there are any questions, you can drop in the chat box.
Yeah. Thank you. And these are the applications of total station. So this is this. See here, this is done actually in our lab. This is done in our lab, where these are the blocks. These are the blocks. Okay, a load is applied on the block. Okay, wherever there is a failure. Okay, wherever there is a failure, that is noted. Okay, that load is already noted, and also the coordinates. How much is the movement? Okay, see these are the points whose coordinates are measured using total station. What are its coordinates after the failure? Okay, what are its coordinates after the failure? So by this we can find out what is the coordinate before the failure and after the failure. So how much it has been displayed, how much it has been moved, that is calculated. Okay, this is part of a MTech project. And also you can see there is a camera here. Okay, the amount of displacement is measured on the screen. Okay, on the screen, and also using total station we have matched with the. So there are two things here. Photogrammetry, this is closely photogrammetry. There is a camera here. Can you see the tripod here? Okay, there is a tripod. This will be taking the photographs continuously or a video continuously, and also this coordinate is measured before the load. The coordinates are measured, and also after the load, after the failure, what are the coordinates? So this is a combination of totalization and photogrammetry. Architectural photogrammetry, as I said, this is a project we have done for City Palace, Udaipur City Palace, okay, where this is completely done using reflectorless totalization. You can see all the white marks here. These are the coordinates measured using totalization. Okay, and this is the ultimately this is a 3D model of the complete Udaipur City Palace. As I said initially, the mapping of landslide. So how much of Earth has been moved? So we are actually the total. This has done very long back, maybe in 2004 or maybe 2004. You can see the date also on the camera. Maybe more than 10 years, around 7-8 years back. So there is a road here. You do because of the landslide. This particular road has been washed away. So we are standing below this. There is a river. Okay, at the bottom there is a river, and we are standing on the other side of the hill, on the other side of the uh, river, and instrument is kept here on the this side, and these are the points where the coordinates are measured using totalization. Okay, and this is the model. Totalization coordinates are taken, and also the photographs are also taken, and this is the 3D model of the complete landslide area. So this is also a combination of photogrammetry and totalization. And this is a contour map. So using contour, we have found out how much is the earthwork which has been slided. Just a small introduction about GNSS. GNSS stands for Global Navigation Satellite Systems. Okay, so there are many constellations are there. Constellation is a group of satellites. Okay, out of which there is a GPS which is launched by US. Along with GPS, there are other constellations called as GLONASS and BIDO. So GPS, GLONASS, BIDO, Galileo from Europe. So these are the different navigation systems. Earlier, only GPS was there, which is fully operational. But later on, we can see that there are other constellation satellites also, such as GLONASS, and Beidou, Galileo, and all. So there are some. There are some. This is the architecture of GNSS. Okay. So any system, maybe it is GPS, GLONASS, or Galileo, whatever, it will have three systems, three components. One is called a space segment, control segment, and user segment. These three will be there in every segment, in every system. Space segment consists of satellites. Okay, satellites. So the most of the GNSS satellites will be orbiting around more than 20,000 kilometers. Right? Around more than 20,000 kilometers of the elevation, these satellites are moving. Okay, and these satellites, like GLONASS, you can see, Beidou, the elevation is around 21,000. Galileo, it is 23,000 kilometers from the Earth's surface. Okay, these many satellites are launched because to calculate the position of any point on the ground. Okay, this our receiver. We have a receiver in our hand, GPS receiver. This should receive signals from at least four satellites, to calculate the position of any point on the ground. So to for having four satellites any time on the throughout the day and at any place on the earth, okay, at any place on the earth, there should be there should be more than four satellites, because if I have four satellites here, whatever the person who is at the other country, so there will be more than dozens of satellites. Okay, because at every point, at any point on the globe, at any point of time, the user should receive, or the receiver should receive signals from four satellites. There was a comment, I just missed it. Can you spell it? IRNSS something is there. I just missed it. Or repost it again.
I'm sorry to peep in. It's an Indian navigational satellite system. Actually, it is more reliable compared to GPS nowadays.
Okay,
And we have almost 7 satellites launched, and we will
yes,
be
sir.
getting.
Actually, yes, sir. You're right. I'm coming there.
Okay.
Actually, these
Thank you.
satellites, these GNSS. Remember, GNSS stands for Global Navigation Satellite System. I'm coming to IRNSS also. There is one slide on IRNSS also. Just hold on. Okay, I'll get back to that. Okay, so these for GPS there are 27 satellites, more than 27 satellites, GLONASS and all. Okay, so these are the number of satellites. Orbital planes. This orbital plane is nothing but the plane of the orbit. Okay, that is called as orbital plane. This orbital inclination is the inclination of the orbit from the equatorial plane. Okay, orbital radius is again 20,000 kilometers. Orbital period means how much time a satellite takes to complete one orbit. So these are the parameters of different navigation system. Control segment. So okay, these are the see here. These are the stations where throughout the globe there are some satellites. These are for the GPS control segment. Okay, these are for the GPS control segment. For every for every system, the control segment is different. The control segment, what it does is these stations. Okay, these are the stations where these stations will be continuously monitoring the satellites, and if any error is there, if they want if any message, or if they will be monitoring the movement of the satellites and also how the satellite signals are being sent to the user. So any updates need to be given from the monitor stations, this control segment, this will be uploaded to the satellites so that users will get the corrected signals. And coming to user segment is all the users who have the receivers. Okay, so we have the receiver antenna, and this receiver our antenna can be used in different types of receivers for geodetic purpose. They are whole and sole geodetic receivers. Okay, in GPS also we have, in smartphones also we have receivers, but these receivers cannot be used for mapping, only for navigation only. For mapping or for for establishing controls, geodetic receivers must be used, which are a little bit expensive. Coming to regional navigation satellite systems. Okay, regional. So these satellites will not have global coverage, unlike GPS, GLONASS, and Galileo. Okay, that is called as global satellite systems, global navigation satellite system, GNSS. These and other system is called as regional navigation systems. Regional navigation system, these satellites will not cover the whole of the Earth. That is the difference. Okay, that is the difference. This is regional navigation systems. Okay, these are launched by specific countries for having more accurate coordinates for that region only. Don't get confused. You cannot say GPS, you cannot compare IRNSS with GPS. That is global coverage. This is regional coverage. Okay, am I clear?